Okay, in the last video, we were recovering what it means to be a predicate, how we sort of think about it semantically, and like what type of object it is in terms of sets, Cartesian products, and subsets. So what we're going to do now is we're going to start talking about interpretations. So an interpretation I is what sets the predicate equal to whatever set it actually is. So we might like say it's this thing here, that whole set that we did up here. But however, interpretations, once you have them set up on your predicates, you can then use them to evaluate formulas. So we might have a formula like, I'm interested maybe in the cats that clean Kit Kat, and I want to know, does every cat clean Kit Kat? So the way that I would evaluate this is I would evaluate what is the interpretation of this given what we already have. So what we do here is we need to evaluate 3 sub-interpretations. We need to evaluate every possible valuation for x, and then we need to figure out, does the resulting formulas give us true in every possible instance of that. So we would have the interpretation of, our interpretation changes a little bit each time. So first we're going to take x and reassign it to Kit Kat. And we're going to ask, does Kit Kat clean herself? Or does x clean Kit Kat? So here we can go ahead and check, does x clean Kit Kat? Where x has been reassigned to k. Kit Kat does clean herself. So we get that this is equal to the interpretation of CKK, which is going to be true. Kit Kat does clean herself. This right here is kind of sloppy notation. I'm kind of abusing notation. You would probably just really evaluate the thing directly, this formula directly. I'm just kind of trying to spell it out and abusing notation a little bit on the way. Okay, so next we would evaluate the interpretation where we actually set x to s. So here we're going to evaluate, does x clean k now? So if x has been set to s, what we're really asking is, does s clean k? So we scroll on up, and we see that we have Sal here, and we have Kit Kat here, and there's this arrow right here. So Sal does clean Kit Kat. We come back down here, and we write that this is true. And finally, there's only one other option for what we could set x to. We could set x to the flufinator. And we again check, does x clean k? So now x is f, so does f clean k? And we come up here, we see, yes, the flufinator does clean Kit Kat. And so, again, this will evaluate to true. So finally, we check, if we set x to k, we get true. If we set x to s, we get true. And if we set x to f, we get true. No matter what, in all cases, we get true. And so that means that this formula right here is true. So a for all x means that no matter what x you set it to, for every possible option, we always get true as a result. Great. There's a similar thing for the interpretations evaluated on existential statements, except now, instead of looking for every case, we're looking to find if there's any one case that makes it true. So maybe we're going to ask, is there a cat who is going to clean the flufinator? And so again, we split off into 3 cases. We have the case where x is k, the case where x is s, and finally the case where x is f. And we're evaluating this subformula here, CXF in each case. Okay, so if we set x to k, does KitKat clean the flufinator? We come up here, we check, KitKat does not clean the flufinator. So this will evaluate to false. Next, we check if Salieri is going to clean the flufinator, and Sal does not clean the flufinator. That would be where that arrow would be. So, but it's not there. And so we say that that is also false. Finally, we check, does x clean f when x clean f when x is the flufinator? And when we scroll back up for that, we see that the flufinator does not clean themselves, and so that is also false. Okay, so now we've checked all three cases. We got false, false, and false, and we're asking ourselves, does there exist some value that we can set x to? Does there exist some value that we can set x to that makes this subformula here true? And it turns out that no, there isn't. No matter what we set x to, we always got false as a result. And so this formula here is going to be false. And so that is an instance of quantifiers. We might talk later more formally about how to do nested quantifiers. And this kind of also justifies our notation here of saying for all for this symbol and exists for this symbol. So when we read this one, we said, does everyone clean KitKat? Is how you would read this. And when we look at the diagram, we can pretty clearly see, yeah, everyone cleans KitKat. Sal cleans KitKat, Flufinator cleans KitKat, and KitKat cleans KitKat. And that's essentially what we checked. Then on the next one, we checked, does there exist somebody who cleans the Flufinator? And we found that no, there wasn't. And this matches informally as well. We look at the diagram, we look at the Flufinator, we see that the Flufinator is just too fluffy. No one wants to clean her, they will get a hairball. And that wraps up our recap of semantics.